Okay, students, here we are back in Calculus BC, and we're looking at section 7.7, indeterminate forms and L'Hopital's rule. So the objectives for this section are to recognize limits that produce indeterminate forms and apply L'Hopital's rule to evaluate a limit. Now, we did a little bit of this last year, so it'll sound fairly familiar. So an indeterminate form of a limit occurs when you attempt to evaluate the limit and find that it produces a fraction, 0 over 0 or infinity over infinity. In order to evaluate a limit of that form, we have to simplify the limit in some way. We did this in the first section on limits by factoring the polynomials or multiplying by the conjugate or something like that, and hopefully finding something that would divide out. For example, if you take a look at the first example where we have 0 over 0, because when we plug in 0, we get 1 minus 1 over 1 minus 1. So then we looked at the fact that we could take the limit and say e to the x squared minus 1 over e to the x, changing the e to the x squared. And so then we have e to the x plus 1. Oh, sorry, we have the limit still. Can't forget the limit. So we're then taking the limit as x approaches 0 of e to the x plus 1 with the difference of 2 squared times the quantity e to the x minus 1. And then that would be over e to the x minus 1. And it's somewhat conveniently, we're able to cancel the e to the x minus 1s. And then we end up with the limit as x approaches 0 of e to the x plus 1, which is equal to e to the 0 plus 1 by direct substitution. We just get 1 plus 1. Therefore, the limit is 2. So we're able to get the limit fairly easily with that one. Okay. However, some limits won't factor in a way where this would work. So when you look at the next one, if we take and we factor the numerator, you can see that factors will not cancel. So no matter what, you're still going to end up with a 2 times 0 over 0, which is still going to be your 0 over 0, which is kind of meaningless, by the way. So we'll talk about this kind of notation because it's kind of frowned upon in AP Calc, but we'll get back to that. So there's nothing that can be done to rewrite that fraction or that function in a way that's not indeterminate. So L'Hopital's rule says, let f and g be functions that are differentiable on an open interval ab containing c, some value c, except possibly at c. Now, you got to remember, we're taking limits. So if there's a hole at c, we can sometimes get around it. That's called removable discontinuity. So that one point, it's called a point of singularity, missing from the function is not a huge problem in calculus. Assume that g prime can equal 0 for all x in AB, except possibly at c itself. If the limit of f of x over g of x as x approaches c produces an indeterminate form of 0 over 0 or infinity over infinity, then. So this is the then. Now here's the if one more time. If your limit can, or your function can be written as f of x over g of x as a fraction, and f prime and g prime exist, or except possibly at c itself, and the limit is indeterminate, then we can apply L'Hopital's rule. Sometimes it's not written in a fraction, but we're able to rewrite it in a fraction form and then apply L'Hopital's rule if we had that case. So let's take a look at the first one. So we have our first situation that is mirrored up above here. So if we take the limit, what we're going to do is we're going to take the limit of the numerator. The limit is x approaches 0 of e to the 2x minus 1 is then going to produce e to the 2 times 0 minus 1, which is just going to be 1 minus 1, which is 0. Okay, there's that check. And then we have the limit as x approaches 0 of just x, which is, of course, 0. There's a check. Therefore, we can say by L'Hopital's rule, sometimes you'll see it L'Hopital's rule or something like that. You spell it different ways, but L'Hopital's rule. Then the limit as x approaches 0 of e to the 2x minus 1 over x is then equal to, we're going to take the derivative of the numerator and the denominator. So in the numerator, we're going to then get the limit, we're going to take the limit as x approaches 0 of the derivative of the top, which the numerator, which is 2e to the 2x, over the derivative of the bottom, which is just 1, the denominator. So now we're able to evaluate this limit, and we get 2 times e to the 2 times 0 power, which is then going to be equal to 2 times 1, which is equal to 2. Okay, therefore, and we'll make this a little shortened here. We're going to say, therefore, the limit as x approaches 0, this out just a tiny bit, of e to the 2x minus 1 over x is then equal to 2. Okay. All right, there's the first one down. Let's look at the next one. And each time we do this, what I'm going to do is I'm going to highlight the fact that as I approach my limit, I'm going to approach it from the limit of the numerator separate from the limit of the denominator to get my zeros or infinities and then put it together with the L'Hopital's rule. Because as I said, when we have the forms 0 over 0 or infinity over infinity, they really are kind of meaningless. So this is what we do. So first step, we're going to take the limit of the numerator, the limit as x approaches infinity of ln of x will give us ln of infinity, which is of course infinity. And then in the denominator, we have the limit as x approaches infinity of just x, which again is infinity. So we have that infinity over infinity form. So then, therefore, by L'Hopital's rule, then we have the limit as x approaches infinity of ln of x over x is equal to the limit as x approaches infinity of, now I'm going to take the derivative of, applying L'Hopital's rule, take the derivative of the numerator, I get 1 over x, and the derivative of the denominator is just 1. So this would be equal to then the limit as x approaches infinity of just 1 over x. And so that turns out to be 1 over infinity, which is equal to 0. So we could say, therefore, the limit as x approaches infinity of ln of x over x is equal to 0. And there you have it. There you go. There it is. Okay. So let me fix this one here and make it a little bit neater anyhow. Okay. So example 1 and 2, let's move on. So we've got applying L'Hopital's rule more than once. So I'm going to make this a little bit bigger here. So we have the limit as x approaches negative infinity of x squared over e to the negative x. So we're going to start out and do the same thing. We have the limit as x approaches negative infinity of the numerator, x squared. That's going to give me infinity. And then I have the limit, that wasn't too fast, the limit as x approaches negative infinity of e to the negative x. So let me be parallel here with my thinking. So it's going to be negative infinity squared for the numerator, which is going to be positive infinity. And for the denominator, I'm going to have e to the negative of negative infinity, which is equal to e to the infinite power, and then that's equal to infinity, of course. So we have infinity for the numerator, infinity for the denominator, right? So that gives us our first application of L'Hopital's rule available to us. So what we're going to do is we're going to say, therefore, I'll pull this down a little bit so you can see the original problem. The limit as x approaches negative infinity of x squared over e to the negative x is equal to the limit as x approaches negative infinity of 2x, taking the derivative of the numerator, over the derivative of the denominator is going to be negative e to the negative x power. And so with this, and that's by L'Hopital's rule. Okay, so didn't state that in there by, so we could just kind of, maybe we'll say it here. And we'll just say L'Hopital. Okay, so now if we look at this one, they'll be equal. But if you look at this, we have the limit, then again, of the numerator. So the limit as x approaches negative infinity of 2x is equal to negative infinity. So then I have the limit as x approaches negative infinity of negative e to the negative x. So that's equal to negative e to the negative of negative infinity. So in the numerator, remember you have 2 times negative infinity, which is still going to be negative infinity. Erase that and put that there. Let me fix that up here. So in the top, where we're doing our direct sub, okay, it's still going to be negative infinity. And then in the bottom, you're going to get the negative of, remember, e to the infinite power. So that's still going to be negative infinity. So you still have a negative infinity over a negative infinity form, right? So now we can do L'Hopital's rule again. So therefore, and I'm going to say by L'Hopital's again, so we're using it twice now. The limit as x approaches negative infinity of x squared over e to the negative x is equal to the limit as x approaches negative infinity of 2x over, so they're applying the derivative of the numerator over the derivative of the denominator. So now we're able to say is equal to the limit as x approaches negative infinity of 2 over, now I've got the negative of negative e to the negative x. I've got one more negative using chain rule, so I have e to the negative x here. Okay, so now I have the, which is equal to the limit as x approaches negative infinity of 2 over e to the negative x. So then that's going to equal 2 over e to the negative of negative infinity, which is equal to 2 over e to the infinite power, which is equal to 2 over infinity, which is equal to, remember, 2 divided by a huge, huge, huge number is just 0. So therefore, we know, and I'm going to put it up here, the limit is equal to 0. So you can kind of see our L'Hopital's rule, where we're able to apply L'Hopital's rule once, and then we're able to apply L'Hopital's rule twice, just kind of making a chain of logic here. It's not necessary you write all that, but, and then finally, with your last direct substitution in, we're able to get that the limit is then equal to 0. Okay, there you have it. There it is. There you go. Applying L'Hopital's rule twice. So now we have the limit as x approaches infinity of e to negative x, square root of x. So the first thing I want to do, remember, one of the conditions in our rule was that we have it written as this fraction like this. So I'm going to see if I can write it as a fraction. And you can very often write expressions in terms of fractions using negative exponents. But in this case, we have a negative exponent. So we're going to evaluate this. We're going to say, let me draw a vertical line just to kind of separate my territories here. So we have the limit as x approaches infinity of e to the negative x times the square root of x. Now, if I look at this, I know that that's going to go to the denominator, and you probably know that at this point as well. So what I'm going to do is I'm going to rewrite it. The limit as x goes to infinity of the square root of x, and that will be over e to the x form. And I'm going to go ahead and take the limit of the numerator. So then I have the limit as x approaches infinity of the square root of x, the numerator quantity, and then, or expression, the limit as x approaches infinity of e to the x. And you can clearly see that both of them are going to be, it's the square root of infinity. It's still infinity. And then in the denominator, you're going to have the limit of e to the x. So it's going to be e to the infinity, which again is infinity. So you have the limits of the numerator and denominator that create the form for e to the negative x, the square root of x, to have an indeterminate form, infinity over infinity. So then, therefore, by L'Hopital's, we'll just say by L'Hopital, by Lop. So then we have the limit as x approaches infinity of, and we'll just write it as the fraction, the square root of x over e to the x, even though it's not the original form. Then that would be equal to the limit as x approaches infinity, kind of moved around just a little bit there, x approaches infinity of 1 over 2 square roots of x over e to the x. Okay. So now if I straighten this out a little bit, which is equal to the limit as x approaches infinity of 1 over 2 square roots of x e to the x, kind of put parentheses around that, if you will. So now if I take and input the infinities, I'm going to get, just by direct substitution, 1 over 2 times the square root of a huge number, infinity, times e to the infinite power. So you can see in the denominator, we're just going to get 1 over 2 times infinity, which is just going to be 1 over infinity, which will turn out to be 0. So our limit of the original limit would just be 0. Okay, see how that is. So rewriting your fraction, rewriting the limit in a fractional form, and then applying L'Hopital's rule. And we get our 0 for the limit. Okay, one more here. We have evaluate the limit here. And this is when we have, sometimes I thought as a student, there's something wrong here, right? Like, why is 1 to the infinite power? Why is it not 1? And it's kind of an interesting dilemma that we get into, but it is not. It's called an indeterminate form. So I'm going to leave it up to you, the reader, to look this up. Why don't you Google this? And maybe we'll start a discussion thread tomorrow on why is 1 to the infinity power not equal to 1. So here's where we're going to handle this. We're going to let, in this one, if you notice, if you put infinity in here, notice what you're going to get. You're going to get 1 plus 1 over infinity to the infinite power. And that's going to leave you with 1 plus 0 to the infinite power, which is 1 to the infinite power. So this is an indeterminate form. So this is where we have to start. Remember logarithms, right? So we're going to be using logarithms for this. So we're going to start, and we're going to say let y equal to 1 plus 1 over x to the x power. Okay? Now, we're going to take the logarithm of both sides of this. So we're going to say the ln of both sides, right? So it's going to be the ln of y is equal to the ln of the quantity 1 plus 1 over x to the x power. Then we're going to take and we're going to whoop this x out front, right? And you know how to do that. Okay, so now we get ln of y is equal to x times ln of 1 plus 1 over x. Okay, now I'm going to look at this for a second. I'm going to say, all right, I'm taking the limit of both sides, right? So I'm going to bring the limit in temporarily. Okay, so I'm taking the limit, I said, as x approaches infinity of ln of y. And that's going to be equal to the limit as x approaches infinity of x times ln of 1 plus 1 over x. You might be thinking, where are we going? We have so far dealt with fractions that we were able to put into the f over g form. So you're like, where do we go with this? So the variable is in both the base and the exponent. So that's why we're going to use logarithms to pull it around, okay? So remember, we're taking the limit now, but I need the limit in a fractional form. Okay, now we're not going to do anything with the left-hand side. We're going to work with the right-hand side. So now I've got the limit as x approaches infinity. And I'm going to do something that's kind of strange that you would not normally do, but I've got to write an equivalent form for this. So the ln of 1 plus 1 over x. And then I'm going to write the x. So I'm going to transform this x. Where am I here? The orange, so I have an x here, right? I'm going to write that in the denominator, as you can guess it, 1 over x. Okay? Now this is indeterminate. If you put an infinity here, you're going to get, for the numerator, you're going to get 0, and for the denominator, you're going to get 0, right? Now I'm not going to do that right now. I could write it, but I'm just going to apply because I'm kind of torn. Maybe we should say it. Okay, let's do it as an aside. I think I have room here, right? So as an aside, so the limit as x approaches infinity of ln of 1 plus 1 over x, and it's already an indeterminate form. You can see from the beginning we spoke about it. Here we're going to get, as x approaches infinity, we're going to get ln of 1 plus 1 over infinity, which is going to, the 1 over infinity will then go to 0 right here. So that'll just give us ln of 1, which we know is 0. Okay, so now we know the numerator is, the limit is 0, and we have the limit as x approaches infinity in the denominator, 1 over x. So we know that's 1 over infinity, which is also equal to 0. So we have the limit of the numerator and the denominator are both 0. So now we can apply L'Hopital's rule. So apply L'Hopital's rule. Scrunch this down just a little bit. So we're able to apply L'Hopital's rule now. So now we're going to take the limit. This limit is then equal to, just going to work vertically with this now. As x approaches infinity, I'm going to take the limit of the numerator, which is going to be 1 over 1 plus 1 over x times, remember, the derivative of 1 plus 1 over x. And maybe I'll just write it like that, d dx of 1 plus 1 over x. A little tight here. Make sure I don't make this video too awful long. And then, how should I do this? Maybe arrows, right? I'll leave that go. And then we'll take the limit. So right now I'm applying L'Hopital's rule, right? So I'm taking the derivative of the numerator, and then I'll take the limit of the derivative of the numerator, and then I'm going to take the limit of the derivative of the denominator. The denominator is a little easier, right? So there. So I'm going to finish the limit of the numerator, 1 over 1 plus 1 over x, and then the derivative of 1 plus 1 over x is going to be the same as the limit derivative of the denominator. So we're going to multiply this by negative 1 over x squared. That would be the derivative here. So just finishing that up here, this derivative is equal to that. So now if I plug this all in, what happens? Is it indeterminate? Let's see. Let's see if we can look at this closely. So it doesn't look like the numerator is going to have a limit that's 0 or infinity along with the denominator. Let's check this out. Because if we write this all together, so if I say all this, let me come down here. This is like an impasse here. playing around here, and without really kind of going into this cold, kids. So here's what I'm going to do. I'm going to shift this over here. It's kind of like, I'm thinking about it, and I'm thinking about it. I'm going to move that over here. I'm going to move this over here. And then I'm going to say, how about if we do this? We're going to say, how about if we just straight out say the limit as x approaches infinity of 1 over 1 plus 1 over x. So I took the derivative and now take the derivative of the numerator, and then times negative 1 over x squared, because I have to use chain rule on that. Okay, and then in the denominator, I'm going to get negative 1 over x squared. So what's convenient about this, once you notice that these two were factors that were the same, you can cancel them. And so you got to remember you have the left-hand side here going on, right? Let's see what we got here. The limit as x approaches infinity then only involves this expression. So we get 1 over 1 plus 1 over infinity, which is equal to 1 over 1 plus 0, which is equal to 1 over 1, which is equal to 1. So now you have to remember what we have going on the other side. Remember, we had the limit as x goes to infinity of ln of y is equal to 1. So really all you have to do is saying as x goes to infinity of ln of y, the expression goes to 1. So all we really have to do is say, okay, then e to both sides, e to ln of y must be equal to e to the first power. And then in that case, then y is equal to e. So now remember what we said in the very beginning. Y, oh, you know what? Yes, y was equal to 1 plus 1 over x to the x power. So we get y is equal to e. Therefore, and we had the limit in there. The limit as x approaches infinity of ln of y is equal to 1. Therefore, e to the ln of y is equal to e to the first power. So we get y is equal to e, and therefore the limit as x approaches infinity of 1 plus 1 over x to the x power is equal to e. Now, we talked about this last year in that chapter on exponential functions and logarithms. So just revisiting that as well. Okay, so that's it for L'Hopital's rule. And then in addition to this, we have some other activities in today's agenda. And that's it for tonight. I will see you when I see you. Have a great day.